Usually, when we talk about defining a loss function in machine learning, there is this underlying assumption of a navigable gradient path.
Right, like a complex, high-dimensional topographical map.
Exactly. You calculate your cross-entropy loss, the gradients flow backward through your network layers via the chain rule, and your optimizer basically looks at that calculus and points downhill. It's saying, the minimum is this way. It's mathematical gravity.
And as practitioners, we find a lot of comfort in that. I mean, we expect loss landscapes, even non-convex ones, to contain localized directional information that guides the weights toward a useful representation.
Right. But step into the world of training deep transformers from scratch for long sequence classification, and that topographical map just completely changes. You are no longer looking at a landscape with the ridges and valleys. You're looking at a space that is, mathematically speaking, entirely flat.
Yeah, the optimization landscape in these specific regimes is the definition of gradient muddy waters. The directional signals necessary to build foundational representations are just, well, they're simply missing when you evaluate the gradients at initialization.
The math tells the optimizer absolutely nothing about where to go.
Absolutely nothing.
Welcome to this deep dive. Since you already spend your days deep in the trenches of machine learning, data science, and applied math, you know firsthand that optimizing modern architectural behemoths is rarely as simple as throwing massive amounts of data at a standard supervised loss function.
Oh, definitely not.
Today, we're undertaking a highly technical, no-fluff exploration of the optimization dynamics specifically within transformer models. We are dissecting a May 2026 paper titled Towards Understanding Self-Pretraining for Sequence Classification, authored by Omar Coser, Loredana Zollo, Paolo, and Antonio Orvieto.
And this paper stands out because it refuses to just accept empirical benchmark successes as a given, The authors actively deconstruct a known optimization anomaly.
Stripping away the complex architectural noise.
Exactly, stripping it down to isolate the exact mathematical bottleneck that's preventing standard supervised learning from succeeding.
And that is our mission for this deep dive. We aren't just looking at empirical benchmarks. We are dissecting why self-pretraining, or SPT, fundamentally alters the optimization landscape to achieve better solutions in sequence classification.
And crucially, why standard supervised training often fails in these exact same environments when given the exact same data.
Okay, let's unpack this. Let's start by establishing the baseline anomaly the authors are investigating. The paper heavily references an empirical precedent set by Amos and colleagues. So let's lay out the parameters of that precedent.
Right. So to contextualize the mathematical proofs Coser and his team developed, we have to look at those empirical findings published by Amos et al. In 2024. The Amos team was running experiments on the long-range arena, commonly known as the LRA.
And for context, the LRA is a benchmark suite explicitly designed to stress test how well machine learning models handle extremely long context sequences. Right.
Yeah, we are talking about tasks involving thousands of tokens per sequence. Things like byte-level text classification, long document retrieval, or flattened image classification.
Which is notoriously difficult.
Right, because handling sequences of that length traditionally wreaks havoc on the quadratic scaling of standard global attention mechanisms.
Oh, wait.
But what the Amos paper demonstrated was that standard transformer architectures could achieve drastically improved accuracy on these LRA tasks, but only if they underwent a very specific pre-training phase first. That phase is self-pretraining.
We should probably define the boundaries of self-pretraining in this specific context because, in the current era of machine learning, the word pre-training usually implies ingesting half the internet.
Yeah, but that is not what is happening here.
Right.
In this specific methodology, self-pretraining relies purely on a masked token prediction objective, much like the original BERT models. You take the input sequence, mask out a certain percentage of the tokens, and optimize the network to reconstruct those missing tokens.
And the critical constraint of the Amos setup, which the Coser paper really focuses on, is that this masked prediction is done without the use of any external data or data augmentation.
Exactly. You are utilizing the exact same finite data set that you will eventually use for your supervised classification task. You simply pass over the training data, first with a masked reconstruction loss, update your weights, and then switch your loss function over to a standard label-based classification loss for fine-tuning.
Wait, if we aren't adding any new external data or using augmentation, why does pre-training on the exact same sequence data help at all? What is standard supervised training failing to do?
That paradox is the exact entry point for the Coser et al. Paper. They essentially ask the same question. What is the actual bottleneck preventing the supervised loss from succeeding on its own?
Because initially, the machine learning community assumed a few common culprits, didn't they?
Yeah, they did. Was the model capacity insufficient? Or was it an issue of severe overfitting, where the model just memorizes the training distribution immediately under standard supervision because the sequences are so high-dimensional?
But the authors ran a series of systematic replications and highly controlled ablation studies based on the Amos findings to test that.
They did, and they methodically eliminated those false suspects. The authors found the central bottleneck in these settings is not simply a matter of model depth or a lack of generalizability.
So if the issue isn't a lack of parameter depth, and it isn't standard catastrophic overfitting, where did their ablations point?
The ablations isolated the failure point entirely to the initialization phase. The core issue is the ability of standard label supervision to learn useful query key attention patterns starting entirely from random initialization.
Oh, interesting. Just right out of the gate.
Exactly. Think about the matrix mechanics happening at step 0. You initialize your query in key-weight matrices using something like Xavier or He initialization. The values are just drawn from a random normal distribution.
So when you compute the dot products between these random projections across thousands of tokens, the variance is incredibly high.
Right. And even scaled by the square root of the head dimension, the resulting pre-softmax values are essentially arbitrary noise. When the softmax operation is applied across a sequence dimension of several thousand, it squashes that noise.
It just flattens it completely.
Yeah, the output becomes a nearly uniform distribution. Your attention map is essentially assigning an equal fractional weight to every single token in the sequence.
It's like trying to learn the complex, localized grammar rules of a new language solely by being given a pass or fail grade on a final essay.
That is a perfect analogy.
Because that is exactly what label supervision is doing in this scenario. You submit a 5,000-word sequence, pool the final hidden states into a single vector, and the loss function just hands back a singular scalar value. Just a low probability score for the correct class.
Right. The network has no mechanism to determine which specific tokens caused that poor grade.
Exactly. But masked prediction, on the other hand, is like practicing by filling in the missing words in a single sentence. The global label just doesn't provide enough local signal to organize the foundational rules of syntax.
What's fascinating here is how that language analogy maps directly to the flow of gradients during backpropagation.
Oh, how so?
Well, when you use a global label, that single scalar loss value has to backpropagate through dozens of transformer blocks and then distribute itself across all those squared interactions in every single attention matrix.
So the gradient signal that corresponds to token A needs to attend specifically to token B becomes infinitesimally small.
Exactly. It is entirely washed out by the noise of the random initialization and the sheer sequence length. Label supervision is demanding that the model immediately construct a global manifold without providing a gradient strong enough to assemble the local coordinate system.
Wow. But the authors didn't just stop at identifying the random initialization bottleneck, did they? They dug deeper into the specific mechanisms of what self-pretraining actually builds that supervised learning cannot.
Yeah, building on the attention bottleneck, the authors delved into their findings using a minimal setup. They wanted to isolate the precise geometrical structures SPT was forming in the parameter space.
And what mechanism did they definitively identify?
They explained exactly how SPT overcomes the initialization problem. It successfully learns proximity interactions.
Let's rigorously define proximity interactions for the listener, because in sequence modeling, especially when your sequence length exceeds thousands of tokens, positional awareness is the entire ballgame.
It really is. By default, the self-attention operation is permutation invariant. The model has no inherent inductive bias regarding sequence order. Treating the data as a sequence or a random bag of words yields the same mathematical result unless positional encodings are injected.
Right, we typically add absolute positional encodings, whether they are fixed sinusoidal frequencies or learned embeddings, directly to the input tokens.
But providing the network with absolute coordinates, simply injecting a vector that represents IM token position 50 and another that represents IO token position 55, does not inherently instruct the attention mechanism to care about the distance between those two vectors.
Yeah, having the positional coordinates is not the same as computing a distance metric. The models still have to actively learn a projection space where the distance between those coordinates dictates the attention weights.
Precisely the point. SPT enables the model to take absolute positional encodings and actively turn them into proximity-biased attention scores. Standard supervision struggles to form this bias organically.
Break down the technical specifics of that for us. How does the math work there?
Mathematically, if we expand the attention pre-softmax operation, we get four distinct terms. The crucial one for learning sequence structure is the position-to-position term.
So that's the positional encodings multiplied through the query and key matrices.
Right. The model needs to adjust the weights such that the specific term yields high dot products when the difference between position A and position B is small, and low dot products when the difference is large.
And the Coser paper found that self-pretraining explicitly forces the model to optimize this exact term.
Yes. SPT forces the weights into a configuration that actively constructs a proximity-biased attention matrix.
We really need to underline the significance of this for the listener, emphasizing how crucial proximity-biased attention is for sequence tasks like those in the long-range arena. When sequence lengths can dilute structural signals, a uniform attention matrix is catastrophic.
It really is.
Think of it like trying to identify a highly specific pattern of connections in a massive, fully connected graph where every single edge has the exact same weight. The gradient signal for the few true edges you actually need is drowned out by the noise of thousands of irrelevant edges.
The masked token prediction objective inherently constructs a banded, almost toplets-like structure. It forces the network to look locally first before attempting to aggregate global context.
Because if the model is forced to reconstruct a masked token, the highest mutual information is almost always contained in the immediate neighboring tokens, right?
Right, exactly. The loss landscape of the mask objective mathematical rewards models that develop strong, local, proximity-based attention weights. The gradient strongly penalizes uniform attention in this scenario.
And standard label supervision just lacks the granular token-level incentive to build that banded attention structure from scratch.
Right. The cross-entropy loss simply looks at the final pooled output and says the overall classification was wrong, providing no specific gradient update that favors localized banding in the early attention layers.
So we know empirically that SPT creates this proximity bias that label supervision misses. But is there a mathematical reason why label supervision can't see this on its own?
Whoa.
Like, is it simply a vanishing gradient problem due to the sequence length? Or is it a fundamental topological feature of the optimization landscape itself?
That transition from empirical ablation to theoretical proof is arguably the most significant contribution of the entire paper. The authors introduce a simplified theoretical setup, moving from empirical ablations to mathematical guarantees.
So they are no longer just looking at absurd training curves. They are making mathematical guarantees about the geometry of the loss surface. What are the constraints of that theoretical setup?
They simplify the architecture to isolate the attention mechanism, analyzing the gradient of the supervised loss with respect to the query and key parameters, and they evaluate this gradient at the exact point of random initialization.
Okay. And what is the core innovation they reveal?
The paper's most profound insight is that under this setup, label supervision is mathematically shown to be locally blind to certain attention score directions.
Locally blind. That implies the directional information is entirely absent.
Yes. If you calculate the gradient of the supervised loss and project it onto the specific parameter subspace that corresponds to building proximity-based attention patterns, the magnitude of the gradient in that direction is essentially zero. It is not just weak or vanishing due to depth, it is functionally orthogonal. The loss surface in those critical, necessary attention score directions is perfectly flat.
Here's where it gets really interesting. If the gradient in a specific direction is zero, the optimizer literally cannot update the weights in that direction.
Exactly. The model is trapped. It fundamentally requires proximity interactions to solve the task, but the supervised loss function is mathematically incapable of generating a gradient vector that points the optimizer toward that solution space.
But contrast this with masked reconstruction, the mechanism of SPT. Because in the exact same theoretical setup, evaluated at the exact same random initialization point, it can detect and optimize along these specific critical attention score directions, right?
Yes, the gradient vector for the masked reconstruction loss has a massive non-zero component projecting directly into that critical proximity subspace. The masked loss illuminates the exact pathways necessary to form local attention.
So the loss landscape for supervised learning isn't just tricky. It is literally uninformative or flat in these specific directional spaces from a random initialization. The gradient for those crucial attention patterns simply isn't there unless you use masked prediction to reveal it.
It's like you're putting on infrared goggles in a pitch-black room. The room didn't change, the data set remained identical, but now the thermal pathways are illuminated.
That's a great way to put it. The topology becomes navigable. And once that path is illuminated, the sequential training strategy finally makes sense. Once the SBT phase has guided the weights out of that flat zero gradient region, you can switch your objective back to standard label supervision.
Because the supervised loss function works perfectly fine once the attention matrices are already situated in a region of the parameter space where local structure is preserved, it simply cannot find that region independently.
So what does this all mean? Let's distill the paper's main contributions for the expert listener. Self-pretraining is not just a regularizer or a data efficiency trick. It is an essential mechanism for navigating an optimization landscape where standard label supervision is locally blind.
Exactly. It specifically serves to initialize query key patterns and convert absolute positional encodings into proximity-biased attention.
It's a mathematical necessity, not just a heuristic performance booster.
And that leaves us with a final, really thought-provoking question directly inspired by the text.
Let's hear it.
If standard label supervision is fundamentally locally blind to these crucial attention directions right out of the gate, we have to ask ourselves, how many other architectural bottlenecks are hiding in plain sight within our standard supervised training pipelines simply because of the loss objective we choose at step 0?
Wow, that is an incredible point to end on. Thank you for joining us on this deep dive. We hope this exploration into the mathematical mechanics of self-pretraining has provided you with new analytical frameworks to apply to your own optimization challenges. And hopefully it reinforces the critical value of constantly questioning foundational assumptions in machine learning. Until next time.